All right. Review. Problem 1. Based on the data shown below, calculate the regression line, each value to 2 decimal places. So far, the online class, the number one error I'm seeing is round off error. Don't do that. Round off error. So 2 decimal places. So how do we do this? Well, we're going to put our X's in a list, and I'm going to put it in L1. Maybe. There we go. And I'm going to put the Y's in L2. And then I'm going to run stat test. And it's what? A lin reg t test. All right. And you could just run a regression on it, which is in the calculate menu. However, you might as well run the test because you have to do that later anyway. Okay, so let's go to our calculators. And let's put that data in a list. And I did. I put the X's in L1, and I put the Y's in L2, and I am going to do a quick check just to make sure that I have all that data in correctly. This is my only chance. As your instructor grading your exams, I can't see what you put in. So this is your chance to make sure it's correct. All right, so I normally, when I do this, I would do a scatter plot. I don't really need to because all they want is the regression equation, but normally you'd do a scatter plot, you'd look at that and all that good stuff. But let's go do our test. So we're going to get out of here. And we're going to go stat tests. And we're going to find our lin reg t test. So is that F lin reg t test? And I hit enter. And I need to tell my calculator what list I'm running this test on. I put my data in L1 and L2. My X data is in L1, so I'm going to second number 1. And I put my Y data in L2, so second 2. And as a reminder, if you don't have your regression equations stored, how do you do that? You go to your variables menu, which is just to the left of clear. You go to the right to your Y variables, number 1 function, and then pick where you want to put it. No, I put it in Y1. Okay, and we are ready to calculate. All right, so the first number they give you in the equation is A, which is the y-intercept, and that is 9.64 to 2 decimal places. And the second number we need is B, which is the slope of the line. It's the coefficient on the X term, and to 2 decimal places is that 1.60. So our equation is 9.64 plus 1.60x. So let's go back and write that in or type that in. There we go. Okay, so we got 9.64 as our y-intercept, and our slope is 1.60. And it does tell me to 2 decimal places. All right, problem 2. You intend to conduct a goodness of fit test for a multinomial distribution with 6 categories. You collect data from 78 subjects. What's the degrees of freedom for the chi-squared distribution for this test? 5. Degrees of freedom is the number of categories, which is 6 minus 1. So that would be 5. Pretty easy test, by the way. Next problem, question 3. We're conducting a test of independence for the claim that there is an association between row variable and column variable. Right, so what's the first thing we need to do? I need to do something before that. Well, I could do that first and then do this, but what do I need before I can calculate expected? What do I need? Oh, come on. I need to add up the rows and I need to add up the columns, correct? Can't calculate the expected without row totals and column totals. So what's the total of row A? Well, if my calculator is correct, that would be 63. 17 plus 41 is 58, 58, and 5 is 63. What is the row total of row B? Would that be 65, 81? Okay, and then we're going to get a total, which is what, 144? Now, what should be true then is that the column totals, when I add those together, I should get 144, correct? Row totals and column totals should equal the same total. So is this what? 26? Can I add? And this was what, 7 and 97? And Z is what, 21? So 21 plus 97 plus 26 should be 144. So once I have the row totals and the column totals, I can go put the observed matrix in, and I can put the expected matrix in. And being the lazy slob that I am, I'm going to let my calculator calculate the expected values. And how do I do that? So expected is what? Is it the row total times the column total divided by the total? So for that first row, first column, is that going to be 63 times 26 divided by 144? Okay, so let's go calculate all of those. I already have, but let's go show you how we do that. Okay, so the first thing we're going to do, bless you. The first thing we're going to do is go to our matrices. So second inverse to our matrix, and I have all of these already in. That first matrix, we had 2 rows and 3 columns, correct? So that is a 2 by 3 matrix in your calculator. So I'm going to go over to edit. And you tell your calculator there are 2 rows, it makes the rows. You tell your calculator there are 3 columns, it makes the columns. And then you just input the, which is different than what I have. Well, I guess I'll put it in. I don't know where those numbers came from. Let's put them in. So what did we have? 17, 41, 5, and then what was the second row? 9, 56, and 16. Does that look good to you? 17, and I always check it. 17, 41, 5, 9, 56, and 16. So the first matrix is good. That is my observed. So now I'm going to get out of here. So I'll do second quit. I'm going to go back in to my matrices. And I'm going to edit number 2 because apparently these are not correct. So I'm going to edit matrix B, number 2. It is a 2 by 3. It's got 2 rows and 3 columns. And then what are each of the elements in these rows and columns? So the first one was the row total, which is 63. Is that correct? Times the column total, which was 26, divided by the total, which was 144. Okay, then we do the row total, 63, times the column total was what, 56, divided by the total, which is 144. And then that last column, the row total was 63. The column total was 21, divided by the total, which was 144. Okay, then we'll do the second row. The second row, the row total was 81. The column total was what? 26, divided by the total, which was 144. There was no times in it. Let's do it again. So 81 times 26 divided by 144. Is that correct? That look good to you? And then what do we have? 81 times 97 divided by 144. And then last but not least, 81 is the row total times the column total was 21 divided by the total, 144. Is that the matrix you guys got? Does that look good? I don't know where I got the answers I got here. That's fine. What did you get different? Which one? Well, we can do it out of the matrix. So like for the first row, first column, that is 63 times 26 divided by 144. 11 point. So you got something different? Okay, let's do it. So that would be 63 times, the column total was 97, divided by 144. 42? What did I have?
I think you may have put it in as 56 instead of 97.
Who, me? Make a mistake? No. That's why I need you guys here, huh? It couldn't be that I'm wrong. Oh, all right, let me do that again. Shh, don't name it down. 63, right? Correct? Times 97 divided by 144. Better?
Yeah. All my numbers are different.
There's one right there. Pick up that.
I looked at it, it's the exact same.
So what numbers are different? Did you print it off yourself or did you print mine off?
I think page 2 is missing. I'm just writing on that.
Oh, okay. Page
Yeah,
two is,
I don't think it printed front and back. It only printed front.
well, then it may be out of order. Did it only print the front?
Yeah, because I'm missing 2, 4, 6.
Oh, yeah, you're right.
Yeah, I'm missing all the even number pages.
Well, oh, you just have to write it. Okay. The next question on the even number page is pretty straightforward. Sorry about that.
BS as well, I'm just realizing.
For which one?
For yours, it says 14.625. I just did it again. Wait, let me do it again.
I got 14.625 twice. These are the numbers that I got the first time and the second time. Well,
No, I'm doing that now, I'm sorry.
no problem. All right, so I think we're good to go. Are we good to go? All right, so what you're going to do in your test is go put these numbers in. And it does tell you how many decimal places. Does it even tell you? 2 decimal places. I am very, very, very lenient on this, but I'm just going to warn you that if it counts it wrong, it could be round off. Because, I mean, you're not going to calculate the chi-squared using the formula. You're going to let your calculator calculate it anyway. So it does tell you to round off to 2 decimal places. So try to remember to round off to 2 decimal places. So this would be 11.38 rounded off to 2 decimal places. This would be 42.44. This would be 9.19, 14.63, 54.56, and 11.81. All right, so now we're going to calculate the chi-squared test statistic, and we're going to let the calculator do that for us. So we're going to go over to stat. Let's get out of our matrices first. We're going to go stat tests, and we're going to find the chi-squared test, which is C, correct? This is not a goodness of fit test. This is a test of independence. So we're going to use the chi-squared test. Where did I put my observed values? I put my observed values in matrix A. So I have to tell my calculator that. So I go second inverse A, number 1. And then I put my expected values in B. So second matrix number 2. And are we good to go here? So now we're going to calculate. And what's our chi-squared statistic? Is it 8.42 to 2 decimal places? And it did calculate the degrees of freedom for us. Why is the degrees of freedom 2? Because it's the number of rows minus 1, which would be 1. 2 rows minus 2 minus 1 is 1. And the number of columns is 3. 3 minus 1 is 2. 2 times 1 is 2. All right. So let's go put that chi-squared statistic in to 2 decimal places. 8.42. All right. Problem 4, I apologize for those that got the one I printed this morning. Choose the most appropriate completion of the sentence. In order to indicate a strong correlation between variables, the correlation coefficient will be near 1. Well, yeah. Near -1 or +1? Yes. So a perfect positive correlation the correlation coefficient R would be 1. For a perfect negative correlation, R would be -1. So the closer you are to 1 or -1, the better the correlation you have. All right, question 5. I wonder if I got this matrix in correctly. Probably not. You are interested in investigating whether gender and major are associated at your college. I'm guessing yes, but the table below shows the results of a survey. So in the columns, we have the genders, men and women. And then in the columns, we have the majors. So this is a contingency table, FYI. So the number of men in math and science majors is 91. The number of women in math and science majors is 102. What can be concluded at alpha equals 0.01 significance level? So what kind of test are you going to run? What's that? You're trying to determine if they are associated. So are you trying to determine if one depends on the other? So does the major math and science depend on the gender? I don't know, we're gonna figure it out. So is this a test of independence? Now it's gotta be either goodness or fit or independence, because we didn't talk about the other two in this chapter. So it's one or the other. It's a goodness of fit test if you're given a table where you have observed values and you compare that to expected. So you have a column of observed and a column of expected, and you run the squared Pearson residual, correct? That's a goodness of fit test. If you have a contingency table, it's a test of independence. All right. So what are your null and alternative hypotheses? So we always state our null hypothesis as what? They're not dependent on each other. So what would that be? College majors and gender are independent. And then what's the alternative? Is that they are dependent. So college major and gender are dependent. All right, so now we're going to go put this stuff in our calculator. So we have what? We have 2 rows by how many columns? 1, 2, 3, 4. So are these going to be 2 by 4 matrices? We're going to put 2 of them in. So we need to, again, get row totals and column totals. Now, if I did this correctly, this is 334. And for the woman row, I got 335. And then for each column, math and science, I have 193. In arts and humanities, I had 209. In business econ, I have 172. And other, 65. So the total, so both the column and the rows should total up to the same number. I got 669. So I need to create an expected matrix. And how are we going to do that? So it's going to be a 2 by 4 matrix. And let's just do the first cell. So first row would be what? 334 times 193 divided by 669. Would that be the first cell? And then you would do each of the cells accordingly. Okay, so let's go put that in. So 2 by 4 matrices. So I'm going to go second inverse, And I do have two of those in there. I don't know if they're correct or not. So let me see what I have in for C. Nope, the numbers are wrong. Well, we'll put the numbers in there correctly. What happened? You know? Gremlins. So we had 91, is that correct? 88. 97. And 58. And then what did we have? 102. 121. 75. And 37. Okay, I'm gonna do a quick check. 91, 102, 88, 121, 97, 79, 58, 37. Since I put the matrix in by rows, I normally check by columns just to make sure I have it in there correctly. All right, so now we're going to go put the expected values in. So I'm going to get out of that matrix and we're going to go second matrix and I put it in D. I never, when I'm taking a test or doing an assignment, delete the matrices till I'm done. I might as well leave them in there because I might want to go back and look and check my work. So I'm going to edit number 4. Okay, and then we're going to put this data in. So what did we have? So we had a row total of 334. Is that correct? Let's see if I can do this correctly. How about it? Times, what was my column total? 193. And divided by 669. So I got 96.356. That looks correct. And then we had what? 334 times 209 divided by 669. That is not, yeah, that's correct. 104.34. And then we had 334 times 172 divided by 669. And that is 85.871. And then what was the last one? 334 times the column total was 65 divided by the total 669. Does that look good to you? Okay, it looks like what I have written on my paper. All right, so in the second row, we have a row total of 335 times a column total of 193 divided by a total of 669. And I got 96.644. The next column, second row, second column, I have a row total of 335 times a column total of 209 divided by 669. I get 104.66. That is correct. So the next one, we have a row total of 335 times a column total of 172 divided by 669. 86.129. And then the last column, I have a row total of 335 times a column total of 65 divided by a total, which was 669. Okay, I'm going to do a quick check. That looks correct to me. Now, you don't have to input this into the problem. So there is no matrix for you to, no contingency table for you to input these values. So be really careful and make sure that you input everything in there correctly. All right, so let's get out of here and let's go run the chi-squared test. So we're going to go stat, test, and find our chi-squared test, which is C. And I put my observed values in matrix C. So we go to our matrix menu, second inverse C, number 3. And I put my expected values in matrix D. So second inverse to my matrix menu and number 4. Does that look good? So let's calculate. Okay, so the chi-squared statistic that we calculated, and how many decimal places are they telling me? 3 decimal places is 13.292 with a p-value to 4 decimal places of 0.0040. So let's go input that. So our chi-squared test statistic to 3 decimal places was 13.292. And our p-value was what? 0.0040. All right, so what do we conclude? So our alpha was what? Alpha's 0.01. Let's write that right here. So comparing our p-value to alpha, is it greater than or less than? It's less than. So our p-value is less than alpha. So what do you conclude? If the p is low, null must go. So are we rejecting the null hypothesis? So there appears to be dependence between gender and major. Does that surprise any of you? So it's going to be one of those sufficient evidences, right? Sufficient evidence to conclude that college major and gender are independent? Nope. There's sufficient evidence to conclude that college major and gender are dependent. And that is the only thing, at least on that page, that's missing. They are dependent. All right. Shall we do another one? That was so much fun. A researcher is interested in investigating whether living situation and pet ownership are dependent. The table below shows the results of a survey. So what kind of test are you going to run? Independence. What are the null and the alternative hypothesis? The null hypothesis is that they are independent of each other. Is that correct? And the alternative is that they are not independent of each other, that they are dependent. Okay, so now what do we need to do? We need to do some totals, huh? Okay, so this is going to be, I have 4 rows and 3 columns. So are these going to be 4 by 3 matrices? 4 rows and 3 columns? And I need to get totals. So I get 210 for the dog row. And the cat row, I got 251. And for the various, I got 157. And for none, I got 152. Which gives me a total of 770. And my column totals also have to add to 770, correct? So I got for single, I got 256. And for family, I got 271. And for couple, I got 273. 4, 5, I think that is correct. So that is my observed matrix. So what's my expected going to be? It is going to be a 4x3 matrix. And let's calculate that first row, first column. So is that going to be 210 times what? 256 divided by 770? Is that going to be that first row, first column? 210 times 2. Okay. Now, I don't want to type. I'm lazy. So I'm going to do a quick cheat. I am going to store 770 in X, and then I'm just going to divide everything by X. So I'm going to go to 770, which was my total, correct? Total 77. 770. And I'm going to store that. The store button is right above your on. And I'm going to store that in X and hit enter. And it'll confirm that it stored it for me. So now when I go put this matrix in and I do all these divisions, I just have to divide by X. I don't have to type 770 in there. These are 4x2s, so that would be 8 times. All right. So let's go to our matrix menu. And I thought it'd be 12 times. Sorry about that. 4x3. I thought I'd put these in E and F, but I'm not trusting myself. So let's go edit E. It's a 4x3. And no, the information is not correct. So 4 rows, 3 columns. And let's put this data in. We have 52, 85, 73. And I was being so protective of that information because I thought I'd put all the review in there. 88, that's right. And then what? 71 and 50, 56, 51, and then 62, 42, and 48. Now I'm going to do a quick check by columns. 52, 92, 50, 62, okay. 85, 88, 56, 42, 73, 71, 51, 48. So my observed matrix contingency table is in. So I'm going to get out of my matrices and go back in. And I'm going to edit F. So number 6. Oops. Clear. I got to edit, not just look at it. Okay, so edit. Number 6. Okay, 4x3, 4, enter, 3, enter. And then what did we have? We had a row total of 210 times a column total of 256. And we're going to divide that by, I put it next because I'm lazy. Okay, then we do a row total, 210 times a column total was what, 271 divided by X. And then we're going to do a row total, 210 times a column total of 275 divided by 770, which I stored in X. I need to do that one again because my paper says 74.455. Let me do that one again. So 210 times 270. It will help if I put glasses on. 273. I think I typed in 275. 273 divided by X. Better. Is that what you got? 243. Well, let's go out and look at it. So I have 73 plus 71 plus 51, 48. 243. Well, piffle. That changes everything. I don't have a pencil. Well, bother. It puzzles me how I got the right answer for the problem if I got a total incorrect. So is the total still 770? Okay. I probably just wrote, I probably wrote it down on my paper wrong. Knowing me, that's what I did. Okay, so let's go back and do that again. So we're going to go second matrix. We're going to edit, and we're editing. I put it in F. So that was, it was 210 times 243, correct? Divided by 770. Is that better? Is that what you guys got? All right, so then we had 256 times 251. Is that correct? Divided by 770. Okay, so we have what? 251 times, what was that? 271 divided by 770. Did you get 88.339? And then we had 251 times 243 divided by 770. Okay. And then what did we have? We have the third row, 157 times the first column total, 256, divided by the total, 52. Yep, that's right. And then we have what? 271. Well, I'm doing it the wrong way. So it's, what row am I in? 157 times 271 divided by 770. Is that correct? Yep. And then what do we have? 157 times 243 divided by 770. So far, so good. All right, last row, 152 times the column total divided by the total. And then we have the row total, 152. And this just points out how you got to really be careful, because I thought I was being careful and I wasn't. Be really careful and check your numbers. And you might even write them down on your paper, because it's the only chance I have to check it. So when you do this calculation and you see it in your matrix, write it down somewhere. on a piece of paper and then I can check it. So what's the last one? Is it 152 times 243 divided by 770? Okay. Think I'm good. All right, so now I'm going to run the chi-squared test. So I'm going to get out of my matrices, second quit, and we're going to go stat, tests, the chi-squared test. And where did I put those? E and F, is that where I put them? So second matrix. At least when I go to the matrix, I can look at the ones that I have there. Does it have the correct number of rows and columns? So it is E, correct? That's the observed, and the expected was an F. Second matrix, number 6. Okay, so how many decimal places? To 3 decimal places, the chi-squared test statistic is 13.840, and the p-value is 0.0315 to 4 decimal places. So the chi-squared test statistic to 3 decimal places was 13.840, and the p-value was 0.0315 to 4 decimal places. And what was alpha? What was it? 0.1. It's right below the table. What can be concluded at an alpha of 0.1? So is that p-value less than alpha? So what do you conclude? You reject the null hypothesis, correct? If the p is low, the null is must go. So we're going to reject the null hypothesis. So what do we conclude? They are dependent on each other, correct? So there is sufficient evidence to say that these two things are dependent. So sufficient evidence to include the distribution of pets is not known. So no. So there is sufficient evidence to conclude that pet ownership and living situation are dependent. Yep. So what are the key words here? Sufficient and dependent. Now, if you fail to reject the null hypothesis, let's just say your problem ends up that you fail to reject it. Let's say your p-value is greater than alpha. Then what do you conclude? There is insufficient evidence, correct? There's insufficient evidence to conclude that they are dependent. So just be aware that I'm not guaranteeing that you won't reject null hypotheses. Okay. Those are literally the most difficult problems on the exam because there's just so much work to them, putting all that contingency table stuff into the matrices. Okay, don't make this problem. A regression was run to determine if there is a relationship between hours of TV watched per day, X, and the number of sit-ups a person can do, Y. The results of the regression equation were Y hat equals A plus BX. A is 32.352. B is negative 0.666. Ooh, that's kind of eerie. And then they give you the coefficient of determination and the correlation coefficient. Use this to predict the average number of sit-ups a person who watches 2 hours of TV can do to 1 decimal place. So what do? It is a plug and chug. So the regression equation is 32.352 minus 0.666x. And what are you going to plug in for x? 2. So y hat is 32.352 minus 0.666 times 2. And what do you get? 31.02 to 1 decimal place. Is that 31? Okay. I have the formula for the squared Pearson residual on your formula sheet, but just to remind you, it is O minus E squared, and that squared seems to maybe not be as large as these old eyes can see. But it's O minus E squared divided by what? E. So you're just going to calculate all the expected frequencies, and then you're going to take the expected from the observed, you're going to square that and divide that by the expected. And how do you calculate the expected? Well, in this particular problem, they give you the probability that you are in that particular category. So what do I need to do first? Do I need to find the total frequency? And then the probability that I'm in category A is 0.15. I take the 0.15, I multiply it by the total, and that gives me how many are in that category. So what's the total? I get 74, but I don't know. Is that what you got? Well, so what's the expected? So let's do it right over here. So is it 74 times 0.15? So what do you get? 11.1? And then what do we have? For category B, is it also 0.15? So is it the same as category A? Is that 11.1? And then what about category C? Is that 0.3? So that'd be twice as much, 22.2? And then about what's category D? 0.4? So 74 times 0.4. So I get 29.6. Is that what you guys get? Okay, now let's calculate each of our squared residuals. So this is going to be 7 minus 11.1, the quantity squared, divided by 11.1. This is going to be 16 minus 11.1, the quantity squared, divided by 11.1. This is 22 minus 22.2, the quantity squared, divided by 22.2. And this is what? 29 minus 29.6, the quantity squared, divided by 29.6. So let's go do one of these calculations. So let's do the first one. So I have parentheses, 7, which is the observed value, minus 11.1, which I calculated from the probability. I'm going to close that. I'm going to square it. And I'm going to divide by the second number, 11.1, the expected value. And I get 1.5141. And they tell me how many decimal places. They report all answers accurate to 3 decimal places. So what would I put in? 1.514. So let's go input all that in here. So I get 1.514 for the first squared residual. For the second squared residual, I get 2.163. For the third, I get 0.002. And for the fourth, I get 0.012. And to find the chi-squared test statistic, I take that squared Pearson residual column and I add them up. And when I add them up, I get 2.691. So the chi-squared test statistic is 2.691. To 3 decimal places. I'm going to give those of you who got a really lousy copy of this, I'm going to give you a chance to write this down. We've got 5 categories, A, B, C, D, and E. And in each of those categories, we have, well, category A, 10, category B, 7, category C, 19, D, 14, and E, 23. You are conducting a multinomial hypothesis test for the claim that all 5 categories are equally likely to be selected. So that means that each category has exactly the same expected value. If they're equally likely, that means each one of them will have the same value. And how do I calculate that value? Do I need to add the total observed frequency? What is that? I get 73, and we take the 73 and we do what? Do we divide it by how many categories we have? 5? So what do we get? 14.6.
The last problem again, the total, the pi squared, I got 3.691, not 2 point.
Seeing if you were awake. You know what I have written down on my piece of paper? 3.691. You know, and the reason I did, though I thought it was a 2, is number 1, my handwriting's bad. And number 2, I don't have my glasses on. Oy vey. Let's fix that. Thank you. What would I do without you guys? I'd fail this test, I think. Something's going wrong with my pins. There we go. All right. See if I can do this one correct. So the squared Pearson residual would be 10 minus 14.6, the quantity squared, divided by 14.6. It would be 7 minus 14.6, the quantity squared, divided by 14.6. We would have 19 minus 14.6. We're going to square that, divide that by 14.6. We have what? 14 minus 14.6. We're going to square that and divide by 14.6. And then we have what? 23 minus 14.6. The quantity squared divided by 14.6. All right, so what do I get? And we're rounding to 3 decimal places again. So I get 1, I will actually put glasses on for this. 1.449, 1.449, 3.956, 1.326, .025 and 4.833. I should probably check that one because I can't read my handwriting again. So I'm gonna do that last one. 23 minus 14.6 squared divided by 14.6. So 23 minus 14.6. Close those parentheses, square that quantity, and divide that by 14.6. 4.833. So I can read my handwriting. So now that we have all the totals, the squared Pearson residuals, excuse me, we're going to add that squared Pearson residual column. Check my math. I got 11.589. At least the big units place, the ones place and the thousandths place look to be correct. All right. Shall we run a regression? Problem 11. And then we get to all the true and false. Right? Now, again, be sure that you do your review to check your true and false to make sure that it's not, it may be worded slightly differently, so that be sure you check yours, do a couple of different of these trues and false so you know what's going on. All right, listed below are paired data consisting of amounts spent on advertising in millions of dollars and the profits in millions of dollars. Determine if there is a significant linear correlation between advertising cost and profit. I would guess yes. Use a significance level of 0.05 and round all values to 4 decimal places. So I have already used my list L1 and L2. And because I'm taking a test and I don't want to delete any data until I'm done, I'm going to put the advertising cost, which is our independent variable, that's our X's. I'm going to put that in L3. And our profit should depend on how much we spend in advertising. So that would be the Y variable, the dependent variable. I'm going to put that in L4. And they give me the null and alternative hypotheses. The null hypothesis is that there is no correlation between advertising cost and profit. The alternative is that there is a relationship. So if rho, that is the Greek letter rho, if rho is 0, that means there's no correlation whatsoever. If it isn't 0, then there is some kind of correlation going on there. Okay? So let's go find the linear correlation coefficient and the p-value and do some comparisons. All right, so let's go put this data in our calculator. Now, I should have it in there, but I am going to go check. And I'm going to make sure I have it in there correctly. So I'm going to go stat, edit. And I should have put this in L3 and L4. So let's look at the cost and see if that's correct. 4, 5, 6, 7, 8, 9, 10, and 11. So I'm good to go there. And then in L4, I put profit 14, 29, 16, 29, 24, 23, 30, 30. So I actually have something incorrect. Woohoo! Pat me on the back. All right, so now I'm going to exit out of my lists, so second quit, and I'm going to go into my stat menu. I'm going to go over to my test, and what test am I going to run? I'm going to run a lin reg t-test, a linear regression t-test. And I want to run the linear regression t-test because I am trying to determine if this data fits a linear regression. And I want to do a test because it'll give me the p-value. Okay, so lin reg t test, and I put my data in L3 and L4, so second 3. Y list, the profit was in 4, correct? L4. My null hypothesis was that rho is equal to 0. So the alternative is that rho is not equal to 0. So that's what you want to make sure is highlighted. I don't necessarily need to store this regression equation because I'm not going to do anything with it. And let's calculate. I mean, technically, if you're a statistician, you would create a scatter plot, look at the scatter plot, create the regression equation, do a comparison, all that good stuff. All right, so what do we get? So the t-test statistic, which we are not going to actually input, but it's 1.870 in case you're interested. The p-value, we are interested in that, correct? And it's 0.1106. And what else are we interested in? We're interested in R, are we not? We're interested in the correlation coefficient. So R is what? 0.6069, because it tells me to round it off to 4 decimal places. So let's go back over to our test and let's input that information. So R, our correlation coefficient, was 0.6069. And the p-value was what? 0.1106. So is your p-value less than or equal to alpha? Or is it greater than alpha? Our alpha is equal to 0.05. So is that greater than alpha or is it less than alpha? Greater than alpha. If the p is high, the null must fly, so we do not reject the null hypothesis, correct? If p is greater than alpha, we do not reject. So what's your conclusion? Well, there's not sufficient evidence to say there's a correlation here. Would you agree? So is insufficient evidence to make a conclusion about the linear? Would you agree with that? And the other thing that you can look at is that R value, the correlation coefficient 0.66, does not indicate that there's a strong linear correlation between the X values and the Y values. All right, and I apologize, you two. These two problems are not on your paper. So problem 11. If the slope of the regression line is positive, then the correlation is also positive. Slope and correlation must always have the same sign. So that is true. So correlation, which we call R, has the same sign as slope, which are we calling it B in this course? So they have the same sign always. Okay, problem 12. This is a problem that indicates that correlation does not mean causation. So a study was done that looked at how much red meat people consumed and how long they lived. The correlation R was found to be 0.98. So there is a strong correlation between how much red meat you eat and how long you live. If it's positive, that kind of means that the more red meat you eat, the longer you live. When a person who does not eat red meat will live longer than a person who has an 18-ounce steak every day, well, there's no. I just because there's a correlation doesn't mean that there's causation. And anyway, it kind of is the opposite of what my correlation is telling me. And the answer is false. No, 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 no. Okay. Problem 13. How much time? I'm out of time, guys, but I'm gonna finish these off. I'll quit talking quite so much. I only got 3 left. If the equation of the regression line for hours X spent cycling in the summer and hours Y spent working in the summer is Y hat is negative 0.7X plus 42, then the number of as the number of cycling hours increases, then the number of work hours tends to decrease. And that is correct. And why is that correct? Oh, yeah, that's correct. Because the slope is negative. It's doing this. And how do I know the slope is negative? Because that number right there is the slope. The slope is the number you're multiplying times the x. So as your cycling goes up, x goes up, you multiply that by a negative, and the overall value for y goes down. So as the number of hours you cycle goes up, well, you've got less hours to work anyways. All right, problem 14. Data was collected on the distance. This is just false. This is just silly. We got to give you one give me, and this is it. Data was collected on the distance from a runner's belly button to the ground, and at time it takes them to run 100 meters. R squared is 0.87. Then 87% of the runners with belly buttons far from the ground run faster. That's just silly. What does R squared actually means? It's the amount of error in your prediction from your R hat regression equation. Okay, and then the last one, a researcher used a chi-squared test for independence where the 2 variables were eye color and hair color, and a p-value was 0.0001 was produced. Then the researcher can conclude at a 5% level of significance that eye color and hair color are independent. Exactly the opposite, correct? So if the p-value is, if the p is low, the null must go. And the null hypothesis is what? That they're independent. So the alternative is that they are dependent, correct? So this shows a p-value that low shows that they are actually dependent on each other. So no, not independent. They are dependent, correct? Are there any questions? All right, well, if you have any,